So our next example involves an inverse tangent function. An inverse tangent function. Before we get to that, though, we do have a product, so you can kind of suspect how this might, in some way, relate to some kind of product rule. Before we do that, I want to notice that I have y squared inside of the tangent. Right? I have a y squared inside of my inverse tangent. So in other words, that's a composite function. Not only do I have that y squared in there, on the outside of my inverse tangent is the stuff that's needed to carry the substitution step through. So here, I want to address that composite function. Rather than starting right now and letting one of these things be u and one of these things be dv, I need to go in here and deal with my composite function first so I can reduce something easier to work with. So typically I come in and let u be my default variable there. So u would be y squared, and du would be the derivative of that, 2y dy. Okay. And so we carry our substitution step through because we have everything we need except for the 2. Easy to account for. Divide by 2 on the outside. And then we're going to have integral of the inverse tangent of y squared. And then we'll have our 2y dy that we need to carry the substitution over to u. Okay. Then I have this integral, which is much nicer and a lot easier to work with than that original. Because if I was trying to do it in this original product, I got a lot of issues. What do I let be what? And how do I approach this problem? A lot of questions there when it's in this format. But recognizing that we can reduce it down, absorb some stuff through substitution down to a new variable, means now we just need to know the antiderivative of inverse tangent. What function do we differentiate to get inverse tangent? Oh, crud. I don't know. I don't know what function I integrate to get inverse tangent. No clue. All right. So, okay, since I can't do, I don't know the integral of inverse tangent, I tried, just like I did with ln there, I tried to do integration by parts. Say, well, maybe this was part of some product that results in inverse tangent. So letting u, not u, I guess now we need to actually go up since we have u as a variable. Let's just do v and w. Let v be the inverse tangent of u, and then let dw be the stuff that's left. In this case, would be du. So we know how to differentiate inverse tangent. It's a mess, but we know how to do it. Right? That's 1 over 1 plus u squared du. And of course, we know how to integrate dw equals du. We'll just get w is equal to u. So since I already had u as a variable here now, then I do my integration parts with the next 2 letters in the alphabet, v and w. Okay? And so now we can proceed because we have it set up for integration by parts. So that will be wv in this case minus the integral of w dv. So the 1/2 still out there. Okay. And then it's wv, so u inverse tangent of u, and then minus the integral of w dv. So that would actually be u over 1 plus u squared du. Okay. So that's straightforward. What about this one here? What about this one here? Well, notice I have u over 1 plus u squared, and u is involved in the derivative of 1 plus u squared. So I can do a substitution step again. Here I'm just going to do it this way. Let v be 1 plus u squared, the denominator. And then dv is going to tell me, hey, you need to give me a 2u to go with your du. If you give that to me, then this will just become integral of 1 over v. Integral of 1 over v. Well, we're almost there. Right? We almost have what we need. Right? We almost have what we need. We have 2u du. That's what we need. We have a u and a du. We're just missing the 2. So rather than rewriting all this again, I'm just going to go in here and say, all right, let's put the 2 that we need there. All right, now I have the 2 there to go with the du. Now I just pulled it out of nowhere, so on the outside I do have to account for that. So by dividing by 2 on the outside. Okay. Then this integral is just going to work out to be 1 over v, and then I have everything accounted for dv. But the integral of 1 over v is just ln. So putting this all together now, we have 1/2 u inverse tangent of u minus 1/2 times 1/2 is 1/4. And again, integral of 1 over v is ln. Ln, absolute value, 1 plus u squared. U squared, yeah. That's where we're at, u squared. And then plus a constant. It's going to be that denominator. And of course, you can drop that absolute value because 1 plus u squared is always positive. And then we have just one more step. So this stuff that we've worked out here, 1/2 and that's the antiderivative of 1/2 inverse tangent of u. So take away the 1/2, multiply these things by 2, and you actually have the antiderivative of inverse tangent. But that's not what we wanted here. We wanted this in terms of y. So we go back and substitute in for u equals y squared. So this will become 1/2 y squared inverse tangent of y squared minus 1/4 ln. Again, we can drop the absolute value and we put y squared in for u. That would be y squared squared. It would be ln of 1 plus y squared, or y to the 4th, sorry, plus a constant. Okay, so now we've worked this out. So two real ideas that came up in this. Here we had something we could reduce first, so let's do that. Makes the thing we have to deal with a whole lot less complicated. That's not to say that maybe you couldn't do integration by parts here, but yucky. I don't know. It's certainly a lot nicer when we come over to this new version of it that has just the inverse tangent. And then we, again, don't know its integral, so let v be that part. All right? And then let the rest of it be your other variable, dw. Okay. And then we carry the process through. This same type of process here works for doing the integral of inverse sine and for doing the integral of the inverse secant function. The inverse secant's a little messier because of how its derivative works. It's a little bit messier, but it definitely works for inverse sine there. So